Good morning, everyone. My name is Dr. Mohit Chaudhary, and I am accompanied with me Dr. Ashna Gupta, who will be taking you through this very important topic called thromboelastography, or which is commonly called as TEG. Now, this has been widely used, and now it's got many applications, right from obstetric cases to liver transplant to end-stage liver disease to cardiac cases, and also in trauma cases. So, this is very important topic. So, let us ace it. So coming to the basics of TEG or thromboelastography, it is a global, that means it covers the entire life cycle of the blood clot. It's a viscoelastic properties that it utilizes of the whole blood. We use whole blood, and this shows the clot formation under low shear stress. So all these words are very important. It is a point of care test in which the interaction of platelets with coagulation cascade is seen. It does not necessarily correlate with the conventional coagulation tests such as PT-INR and APTT and platelet count, but nonetheless it gives you the full and whole life cycle of the blood clot. So how does it work? So basically there is a pin and a cup. This is a basic model in which there is a pin which is suspended through a torsion wire. If you can see here, this is a pin, and through the torsion wire it is suspended, and there is a cup which is going to be moving around the pin. Now this cup, what we do is we fill it with the blood, but before that we have to maintain the temperature here. So 37-degree temperature, which is the body temperature, it's like a heated cup at 37 degrees Celsius. So the whole blood is suspended inside it, and there is a pin. So as there is a clot formation, and this is oscillating at all times. So as there is a clot formation, this pin gets attached to this cup and it starts moving, and this creates a signal or an electric signal which is produced, which is then changed into a graphical signal and a numerical output, so that we can actually see the whole life cycle of the blood clot. So what is the method? We generally take 0.36 ml of whole blood incubated at 37 degree in a heated kaolin containing cup. Now kaolin, what will it do? It will start the process of intrinsic coagulation pathway. Now pin is suspended into cup and connected to a detector system through the torsion wire, like I said. Cup is oscillated at an angle to the pin. The fibrin forms between the cup and the pin, and that is how they get attached to each other and they move together now. So the formation of fibrin results transmitted rotation from cup to the pin. This causes an electromechanical transduction system or optical system, with result displayed as a graph or what we call generally as a trace as a result of pin's movement. Now pattern and duration of different aspects of tracing provides information on the clotting and the lysis process. These are the various instruments that are there which are available. The other viscoelastic test is along with TEG is the ROTEM or rotational thromboelastometry. So you, depending upon which you have in your institute, you can use that. But more common in this part of the world is TEG. So this is a TEG 5000, if you can see, and this is ROTEM delta. This is TEG 6S, and this is again a ROTEM sigma. So you have these cups which I was talking about, in which the pin goes. So this is the cup which is very used generally. So now I will hand over the thing to Dr. Ashna, who's going to talk to you about the various factors and assessed in this thromboelastography, right from clot formation to clot kinetic to clot stability to clot resolution. In this episode, we will generally cover the tracing and the various types of tags that are involved. So after that, we'll have another episode on the various case scenarios in which tag is used, and then we will have a Q&A session on the same. So over to Dr. Ashna, who is going to take you further.
Good morning, everyone. I am Dr. Ashna, and I will be talking about thromboelastography. So, thromboelastography is a measure. It is a test of blood coagulation. It is a viscoelastic test. It measures the efficiency of blood coagulation. So, it assesses all components of thrombus formation, that is clot formation, clot kinetics, clot stability, and clot resolution. So in normal APDTPT, that is conventional coagulation assays, we only know whether the clot is formed or not, but we don't know how fast is the clot forming, how strong it is, and how long it is lasting. So all these components are assessed by uh, thromboelastography. So it measures the dynamicity of blood coagulation. This is a thromboelastogram showing all the five variables, that is the R time, the K time, the alpha angle, the MA, that is the maximum amplitude, and lysis 30. So we can divide this thromboelastogram into coagulation and fibrinolysis. In coagulation, we know how the clot is forming, and in fibrinolysis there is clot resolution. So R time denotes the clotting time. Clot kinetics is measured by the K time and alpha angle. This is the MA, maximum amplitude, that is the ultimate strength of the clot, and this is thrombolysis, that is lysis 30. That is how stable is the clot, how last it is longing. Now, one by one, we will discuss each of these variables. First is the R time. So, when we add whole blood into the cup and the time it takes for the initial fibrin formation, that is denoted by the R time. So, it represents the period of latency from the start of test to initial fibrin formation, and its normal range is 15 to 23 minutes in native blood when we are only adding the whole blood, and if we add an activator like choline, then it is 5 to 7 minutes. It represents the initiation phase of cell-based model of coagulation. So this R time, it is dependent on clotting factors. So it is increased if there is any clotting factor deficiency in anticoagulants, if the patient is on any anticoagulant, or severe hypophiltration, and it is decreased by a hypercoagulability syndrome when there are too many clotting factors. So our time is less as there is fastly the clot is forming. Now K time, it is the time to achieve a 20 mm clot strength. So we are seeing the time the clot reaches its 20 mm strength. From 2 mm initially the clot has been formed, that is measured by end time. Now how much time it is taking to achieve this 20 mm clot strength, that is measured by K time. So it is dependent on platelet, but it's also dependent on platelet also, but mostly it is dependent on fibrinogen. It represents the amplification phase of cell-based model of coagulation. Its normal range is 5 to 10 minutes in native blood and 1 to 4 minutes in choline activated. So it will be increased if there is any factor deficiency or hypofiltration, as it will take more time to achieve 20 mm clot state, and it will be decreased in hypercoagulability state. Now alpha angle is the speed at which this fibrin buildup and cross-linking takes place. So it measures the rate of clot formation. Now it is the speed at which the fibrin buildup takes place. K is the time to achieve 20 mm strength, and alpha angle measures the rate of clot formation at which speed the clot is forming. It is dependent on fibrinogen, and it represents the propagation phase or the thrombin burst. Its normal range is 22 to 38, and its angle is increased by hypercoagulable state, and it is decreased in hyperfibrinogenemia or thrombocytopenia. Now the maximum amplitude, it represents the ultimate strength of the fibrin clot, which is a direct function of platelet and fibrin bonding by a GP2B3A receptor. So this is the MA, which represents the ultimate strength, like how strong or how strength the clot has. It correlates to platelet function, that is 80% by platelets and 20% by fibrinogen. Its normal range is 47 to 58 mm in native blood and 59 to 68 mm in choline activated. and it is increased in hypercoagulable state, and it is decreased by thrombocytopenia, thrombocytopathy in platelet function defect, and in hypofibrinogenemia. Now fibrinolysis, lysis 30. Now the clot has been formed. After 30 minutes, we are seeing its decrease in amplitude. It measures the percentage decrease in amplitude 30 minutes post MA. Its normal range is less than 7.5%. We also have lysis 30. Like after 60 minutes, we take this value. This is the diagram showing correlation of TEC with the coagulation cascade. So the coagulation cascade, we know there are two pathways. There is an intrinsic pathway and an extrinsic pathway. So intrinsic pathway is activated by a contact factor and extrinsic by tissue factor. So this pathway leads to a common pathway which activates the thrombin by activating prothrombin, and this thrombin then activates fibrinogen to fibrin. So there is initial fibrin formation, that is clot formation, that is measured by R time. So as you can see, it is mostly dependent on the clotting factors. So now the conventional coagulation pathways, that is PT, APTT and PT. APTT denotes the extrinsic pathway and PT denotes the extrinsic pathway. So this only tells us whether the clot is forming or not. It will not tell us about the clot kinetics, how fast the clot is forming, how stable is our clot, how long our clot is lasting, that is fibrinolysis. So all these we can know by thromboelastogram, which measures the efficiency. But as compared to PT and APTT, it only measures whether the clot has been formed or not, and it is correlated. It can be correlated with the R time, which denotes the initial fibrin formation, which is dependent on the clotting factors. Now clot kinetics, that is the K time and alpha angle. Now the fibrin has been formed, it is getting accumulated. Thrombin also activates factor 30, which leads to fibrin polymerization. So this fibrin polymerization, it is the alpha angle, that is how fast the speed of fibrin accumulation, that is the rate of clot formation, that is the fibrin polymerization. And the K time, it is the time to achieve a 20 mm clot strength, that is the K time. Now our clot has been formed. Now clot strength and stability, it is determined by MA. Now fibrinogen will interact with platelet to form a stable clot by GP2B3A receptor, that is measured by MA. The ultimate strength of the clot is the maximum amplitude. Now clot resolution will take place, fibrinolysis will occur, that is denoted by lysis 30, that is 30 minutes after clot formation we see lysis 30, and lysis 60 is after 60 minutes that we see. Now, this is the normal coagulation cascade. Now, the cell-based model, how TEG is related to all the three phases of cell-based model of coagulation. We have in cell-based model three phases, that is initiation, amplification and propagation. So, in initiation phase, we know in cell-based model, the extrinsic pathway will activate the intrinsic pathway. So, in first initiation phase, the tissue factor is released after injury. It will activate factor 7. Factor 7 will activate factor 10, and this will lead to activation of thrombin. So this initial thrombin that has been formed, which will lead to finally fibrinogen, initial fibrin formation, that is the R time, the initial fibrin formation is denoted by R time. Now we have K time. The K time is the time to achieve a 20 mm clot strength. So now the thrombin that has been formed, it will activate the platelet, and it will activate other coagulation factors like factor 8, factor 11. So all this will result in formation of activation of thrombin. So this is the amplification phase. That is to achieve a 20 clot strength. That is the K type. Now we have alpha angle. Now the thrombin that has been, now the coagulation factors that are active in intrinsic pathway like factor 11, factor 8, this will lead to a lot of thrombin generation, and lot of thrombin generation will lead to thrombin burst that will cause increase in fibrinogen formation, that is fibrinogen to fibrin conversion. That is the alpha angle, that is the thrombin burst or the propagation phase. Now a clot has been formed. The fibrinogen will interact with the platelet for the ultimate strength of the clot, because now fibrinogen has lead to formation of the clot. Now platelet will provide additional stability, additional strength to the clot. So that is the maximum amplitude, the ultimate strength of the clot. Now the our plot has been formed. Now after 30 minutes we will see the percentage of lysis. The fibrinolytic system like the tissue plasminogen activated will get activated, and it will cause clot resolution. That is the percentage lysis 30. So this is just a summary table showing all the variables of the tech. So first we have R time. We know that it is the time for initial clot formation. So if it is high, we know there is problem in coagulation factors. So we will give FFP. And if it is low, then we know there is hypercoagulation. So we will give anticoagulants. K time, it is the time to achieve a fixed strength, that is 20 strength. If it is prolonged, we know there is problem in fibrinogen, and if it is shortened, then there is hypercoagulation. So if it is prolonged, we will give cryoprecipitate, and if it is shortened, we will give anticoagulants. Now alpha angle, it is the speed of fibrin accumulation. We know if it is low, then there is problem in fibrinogen, and if it is high, then hypercoagulation. So if it is low, we will give cryoprecipitate. Now maximum amplitude, it is the maximum strength of the clot. 80% it is dependent on platelets and 20% on fibrinogen. So if it is low, we will give platelets, and if it is high, we will give anticoagulants. Now lysis at 30 minutes. This is the percentage of lysis of clot 30 minutes after maximum strength. So if it is high, that means excess fibrinolysis is going on. So we will give excess fibrinolysis is going on. That means the patient can also bleed. So we will give antifibrinolytic agent, that is tranexamic acid. And if it is low, that means there is decreased fibrinolysis. So we can give tissue plasminogen activator. So these are all the traces. This is a normal trace. You can see normal R time, K time is normal. There is normal maximum amplitude. As compared to this, you can see in this the R time is so prolonged. So there is problem in clotting factors. So patient can be on any anticoagulants, or patient can be hemophilia, or there is any factor deficiency. So we will give FFP to this patient. Now this third, you can see R time is more or less normal, K time is prolonged, and angle is also normal. MA is basically reduced in this. As compared to this, MA is much reduced. So there is problem in platelets. Patient can be a thrombocytopenia, there can be a platelet function defect. So we will transfuse platelet to the patient. Now this fourth, we can see there is increase in fibrinolysis. So R time is normal. There is MA, there is continuous decrease. Ultimate strength has been achieved, but it is not longing last. There is persistent decrease in MA. Lysis 30 is greater than 7.5%. So excess fibrinolysis is going on. So we will give this patient antifibrinolytic agent, that is tranexamic acid. Now this graph, we can see there is huge increase in MA. R time is so less, K time is decreased, the angle is increased and the MA has also increased. So we can interpret that the clotting factors are very much activated. Clot is getting formed at a faster speed. Alpha angle is also increased, so there is increase in fibrin accumulation also. MA is also increased. So this is showing hypercoagulability. So we will give this patient anticoagulants. Now DIC, there are two stages in DIC, that is stage 1 and stage 2. In stage 1 you can see the R time is less, K time is also less, alpha angle is increased, MA is also increased, and there is fibrinolysis, secondary fibrinolysis. So this is stage 1. Now in stage 2 there is consumptive coagulopathy, that is all the coagulation factors have been consumed now. So the patient will go into a hypocoagulable state. R time will increase, there will be decrease in MA, decrease in alpha angle. So this is a stage 2 of DIC, that is hypocoagulable state. Now we have various types of TEG also. We have standard TEG, that is Coagulation. In this we take whole blood in the cup, and Coagulation, the reagent that we add, it contains Coagulation activator. Now we have rapid TEG. It contains, the reagent contains both the tissue factor and Coagulation as activator. So this assays both the tissue factor initiated and the contact pathway initiated coagulation, and it provides information similar to PT and APTT, and it is much faster than Coagulation activated. Now heparinase TEG, the reagent contains a Coagulation activator and it contains heparinase for neutralizing the unfractionated heparin. So if we have to neutralize the heparin effect, we use heparinase TEG. If the patient is on heparin and we have to neutralize the heparin effect, so we can use this heparinase TEG. Now we have functional fibrinogen TEG. So if we want to see the contribution of fibrinogen to clot, we will add a tissue factor and we will add apiximab, that is a GP2B3A inhibitor. So we will block the platelet contribution of the clot to the clot, so we can only see the contribution of fibrinogen. So this assays qualitatively assess the contribution of fibrinogen to clot strength independent of platelet. Similarly, we have TEG platelet mapping. It is used to assess platelet function and the effect of antiplatelet agents. So this reagent contains ADP or arachidonic acid, which activates the platelet. Now we have native TEG. In this we don't add any activator. It is impractical for clinical use given their long reaction time on the TEG analyzer. Thank you so much. This is all about TEG.